New nuclear is on the horizon and can provide an effective zero-emission solution for heavy industry and transport, which are currently responsible for as much as 30% of all greenhouse gas emissions. To achieve this, nuclear needs to move from economies of scale to economies of numbers. Nuclear power is a true zero-emission technology, and it needs a mass market. Ocean transportation is a vital component of global trade, with over 85% of commodities, industrial components, and durable consumer goods transported at sea. Of the world's 100,000 ships, just 7,300 consume half of all marine fuels, and thus emit 50% of all greenhouse gases from ocean transportation. From 2050, the UN has mandated that ocean transport must be emissions-free. In 2018, Core Power was formed to bridge the gap and build the market for advanced nuclear technologies in the maritime industry. Today, Core Power partner with leading international companies to deliver durable, zero-emissions energy solutions for floating industrial production and deep-sea shipping, while also co-funding developments of advanced nuclear energy technologies which are appropriate for maritime use and lead the work to build commercial civilian nuclear solutions for shipping. Our industry engagement, regulatory consultation, design and engineering will result in a competitive, true zero-emission power system for the future of maritime from 2030. Core Power are actively participating in the work required to modernise regulations for maritime and nuclear, and to pave the way for small-scale nuclear to take its rightful place as a key pillar of global sustainability.
Hello everyone, greetings from West London and welcome to all of you for this month's online programme, which is now the fourth in the Core Power Hour series. This is currently a free-to-attend event which provides a taster as to some of the learning element of our client programme series of events. Now, as Zoom always reminds me, it's good practice to confirm right at the outset here that this programme is being recorded, and we'll be able to provide a copy of the recording in due course. So if you would like one, please let us know. And the same, in fact, goes for all of the previous editions of the Core Power Hour as well. Now, a small housekeeping point is that we would respectfully ask that you don't take screen grabs from the presentations. If there is a specific image that you'd like to see again, please contact us offline and we'll do our best to assist. For those of you that haven't joined one of our programs before, my name is Toby Menzies. I'm responsible for Core Power's client program, and I will be your host and moderating our panel for today's event. Now, we've previously covered the use of advanced nuclear power technology offshore to produce low carbon synthetic fuels for shipping. And we've looked specifically at nuclear electric propulsion for the container ship segment. And last time we looked at the very important topic of safety. Now, today's program is linked to safety, which is why we wanted to place them back to back in the program. But whilst the two subjects are intertwined, they're not exactly the same. So we'll do our best today to unpack as many themes and threads on maritime nuclear security as we can. Now, like safety, robust and effective security protocols are an absolute prerequisite for any nuclear site. Security of a nuclear site that is also situated at an offshore location, or in the future even on a commercial vessel, poses additional challenges, as well as some additional natural defences that the operator can use to his or her advantage. And we'll try and look at as many of these nuances as we can in the time available today. And there will also be the opportunity to answer some questions. So if you do have something that you would like to ask or to have clarified, please use the Q&A function on your screens and we'll do our best to get through some of these. We may be able to provide a quick written answer to some, and others we can try and answer in person. Now, joining me, our three panelists today are our Chief Executive, Mikhail Bo, Yanis Kouratis, who's one of our nuclear engineers, and Giulio Gennaro, our Technical Director. So welcome, gentlemen, to all of you. Now, Giulio, I believe you're going to start the discussion for us today and to sort of provide a backdrop, if you like, and to do some scene setting for us of some of the major themes. So what is it about nuclear security in a maritime context that you think is sort of most important to get across today? Giulio, if you could unmute yourself, that would be great.
Okay. Can you hear me now?
Yes, all good.
Okay, so as I was saying, it is very important talking about nuclear security that we understand what are the threats that we might face. And there are basically two main threats. One is the possible weaponization of either fissile material or radioactive waste, which could be then used for, let's say, noxious uses outside of the nuclear plant, and the weaponization of the nuclear facility itself, either through an attack meant to cause an accident or an attack meant to seize the facility and then either cause an accident or result in theft of fissile material or radioactive waste. There is also a third category of threats that we might be facing, which attacks meant to cause operational disruptions. Now, this could be, let's say, a real attack, as we have seen in the past, preemptive strike against country infrastructure, nuclear facility, but this can also mock demonstrative attack by anti-nuclear protesters that are meant to disrupt the operation without causing real harm to the facility. Looking at the threats, we also need to examine the possible origins, the axes, and the vectors of these threats. So origin possibly could be hostile states. This could be a war risk, even though this action might not necessarily be act of war. Again, we might quote preemptive strikes we have seen by, for instance, by Israel against Iran. But of course, these are not war risk, and these kind of threats are not really, let's say, the domain of the nuclear security of the operator, which would be instead, let's say, terrorist or criminal attacks, ideological demonstrative attacks, and we have also seen in the past part of, let's say, members of the personnel of the station that decided to commit suicide and decided to do it in the power plant to have, let's say, an echo on the media. Talking about floating or power plants or ships, of course, the axes are multiple: air, surface, and even subsurface. And as far as vessels, as vectors, we can see manned or unmanned vehicles, especially in the second Nagorno-Karabakh war, and now again in Ukraine, we see how drones are being extremely effective to carry out strikes, but also squads or even single men. Now, how can we mitigate the risk posed by these threats? Well, the first mitigation principle, as far as security goes, is to make a nuclear facility a very low yield target. And as a matter of fact, we've seen that in the past, despite attacks to nuclear facilities, the outcome of these attacks has been relatively limited. How do we do this? First of all, we need to select nuclear technology which mitigate safety and security risk. This is very important. A safe installation is also installation that is easier to make secure. And then we need to implement a set of passive and active measures and barriers to further mitigate the risk. We cycle back to security by design principle and safety by design principle. So basically, no single point of vulnerability, maximize the spatial and physical separation between the different components, and reduce the potential path for attack. Risk mitigation strategy going, let's say, in respect to the different weaponization risk, we can select proper proliferation-resistant fuel. Of course, we have a wide, let's say, selection of fuels available, even if we're discarding high-enriched uranium, but we have low-enriched uranium, high-assay low-enriched uranium, and also thorium. And again, there are different considerations in this respect. Select nuclear technology with long fuel cycle. Why? Because this would allow to lengthen the time between the need to handle the fuel and the waste, eventually also choosing technologies that allow to handle the fuel and the waste only at commissioning and decommissioning, so thereby not handling the fuel during on board during the operational life of the vessel, and thereby reducing the possibility of leakages of this radioactive material outside of, let's say, the supposed logistic chain. And finally, lock the fuel and the waste inside the reactor, inside the facility, making them inaccessible. As far as mitigating the weaponization of the facility itself, again, as we said before, select nuclear technology which are fail-safe and passively walk-away safe. So if something happens, we can really shut down completely the facility, or the facility shuts itself down in a sense as soon as it senses that something is not as it's supposed to be. Providing barriers. There are physical barriers, but also, let's say, areas with security zones, monitoring and sensors, provide security detachment, and also a layer of cybersecurity, which is becoming more and more important. Also providing safeguard against internal tampering, because we see that threats could come from the operator themselves. That means proper vetting, proper training, and control on their mental health. Restrict access to sensitive areas, and also provide, we believe that this is extremely important, remote monitoring, control, and shutdown possibility from remote control room away from the facility themselves. Now, the current security framework by the International Atomic Energy Agency sees a very wide range of publication, nuclear security series, and S1 to 43, comprising the entire chain, logistic chain, from the fuel production to the shipping of the fuel to the operation of the plant themselves. While in the marine domain, we have, of course, the International Ship and Port Facility Code, also known as the ISPS code, which is part of SOLAS, which provides a comprehensive mandatory security regime for international shipping, and which is also being implemented by cybersecurity. So by marrying these two security framework, we will be able effectively to manage the security for nuclear marine installations. Thank you, Toby, back to you.
Thanks, Giulio, very much for that introduction. I think that's a great overview, and indeed, it does set the scene for today's talk very neatly, I think. It's a strong starting point, isn't it, when you have that naturally proliferation resistant fuel and, that married with long or indeed ultra long fuel cycles. Now, I'd now like to bring in some other colleagues who are joining today. Firstly, Mikhail, I know you have a handful of slides to present as well, but if I could start sort of by asking you, because I think this follows on a little bit naturally from Giulio's talk there. Security is generally not the first question that arises when we discuss the technology and its application for maritime, but it is something that often comes up relatively early in the discussion, and it's often along the lines of, what if X happens, what if Y happens? And I guess, the practical application of security protocols themselves is really a series of what ifs. So I would sort of ask you, how would you summarize what you've learned over the last few years when considering the overall security picture for new nuclear and maritime?
Thanks, Toby. What we've learned over the last few years, of course, is how complicated and complex this is. Looking at the entire picture, and it, of course, has to be approached from a practical perspective. We do get a lot of questions which are, absolute worst case scenarios, everything from from the sort of the ridiculous to the sublime. And of course, there is a well-trodden path for how these things are managed. But it does come down to case-by-case basis when we're looking at specific implementations of floating nuclear power plants, nuclear ships in various jurisdictions, et cetera, et cetera, et cetera. So I think what I'd like to show here is a little bit about the functional and regulatory introduction to this, so that we're focusing on the functional and the practical side of this as well. And I really wanted to try and show a little bit today what as Giulio sort of set the scene, what the real essence of this is, and show that this is as I said before, a well-trodden path. This is not something that we're starting from scratch with. This is not something that is a brand new challenge. It's something that's been dealt with by the international community and nuclear operators, nations, etc., for about 70 years. So a lot has been learned. A lot of mistakes have been made, and we learned from those. And of course, we have a very broad and very detailed framework for how this actually works. Now, in the International Atomic Energy Agency's security fundamentals, the kind of rules that sets down what this really is all about. Nuclear security, as Julia pointed out, is really defined as the prevention of, the detection of, and the response to these criminal or intentional unauthorized acts. Involves the material, facilities, and also activities around that. But importantly, and I think this really plays to the narrative around how this new nuclear security for maritime works, is that nuclear security, as defined by the members of the International Atomic Energy Agency, that's the UN agency that deals with these matters, is that it is ultimately the responsibility of the state to set the security requirements for nuclear power stations in their countries. And of course, now, if that is a floating nuclear power plant, which is either operating in the waters of the country or it's a nuclear ship flagged in the country, that then is passed through the flag state. So the responsibility of the state is reflected in the flag state. So if you have an American ship, US flagged ship, it would be US security regulations that would be, and requirements that would be applied to that vessel. So in the UK, with Japan, other nations as well. And the IAEA supports those states then, in how to do this through a nuclear security program. And that nuclear security program provides legal instruments, so specific legal instruments for dealing with this, enforcement, if you like, protection of information, which is very important, making sure that information about where things are and how they can be accessed, etc., is hidden away and kept from bad actors. Physical protection, as you can imagine, that's not just in security guards and personnel lookout, it's also in the way that we build these things and provide sort of no access to material and to machines, and of course material accounting and control, knowing where things are at all times, and being able to maintain a sort of inventory of the fuel. Detection and response is important, national response plans, of course, and then contingency measures. All of these things are well defined and constantly debated, constantly brought up to date, and constantly worked at the international community level at the IAEA. But there are three essential measures that the IAEA says, this is all about. So it's unauthorized removal of material and use, storage. It's sabotage of facilities and material during transport. And this is a vulnerability that, is there, because once you've taken either, fuel to be moved towards a reactor site for refueling, or the spent fuel that comes out that's taken back either for storage, for reprocessing, creates certain pockets of vulnerability in the security of that fuel. And then, of course, the final one is sabotage of facilities of materials then in storage. So, avoiding that to a greatest extent possible is really what we have to ask ourselves, how this applies to new nuclear. So if you're looking at unauthorized removal of material, use and storage, it's really those active measures in material accounting and control. So knowing how much fuel is there at all times and making sure that doesn't change from one control to the other, and predicting that the material will still be in the same place going forward. So it's really real-time accounting and control of nuclear materials, and of course then detecting and planning for what could happen if there was some sort of subversion around that. Julia mentioned insider measures, so this is insider threats from personnel or from people who've sort of embedded themselves in the crew of these to perform malicious acts, and that checks the cultures and that inability to operate alone. These sort of checks and balances that can be put in place to make sure that there really isn't an opportunity for a single actor to actually do something. And of course, passive measures from access restrictions, I think, are very important, the way that this is designed. My colleague Yanis is going to be talking a lot about this later on, this idea that strength and defense and depth of design, this, like a safe room in a bank, it's not easy to get in there once it's locked. And it's not just the room, it's getting to that room as well, which is in terms of sabotage of facilities and material during transport, it's active measures in threat detection, communication, physical defense. So, making sure that that's a constant 24-hour, lookout system, everything from electronic systems to people looking at things. And then, of course, again, those that training and culture and the physical restrictions for insider threats to be mitigated. And then passive measures from strength and defense and depth of design. Again, Yannis is going to be talking about this. And these passive fail-safes that Julia mentioned that enables systems to shut down, without any operator interference if something is not right in the system. So that sort of renders things safe and secure without the need for somebody to actually do that directly. And with this comes, 4 specific levels of detail from the International Atomic Energy Agency. We got nuclear security fundamentals, those basic fundamental rules that exist and are passed through the states for them to implement to make sure that nuclear security is at all times maintained, and then recommendations, implementation guides, and then specific technical guidance related to specific technologies or specific sites or specific situations that might exist there. The IAEA, most of us in the shipping industry are not too familiar with what happens on the nuclear side, but the IAEA was, it was formed back in the 50s, 1957, and it was really a response to fears and expectations generated by nuclear technology. We had of course, the Second World War, where this was demonstrated to great effect in the weapons program, but that this, following the war and the Atoms for Peace program that President Eisenhower of the United States put together in 1953 really, set this up to show that, how this could be done in a peaceful way. And that's really what the IAEA is there to do. It's Atoms for Peace and making sure that everything is done right. And of course, security then comes as an important part of that. So we can be confident that the international community is very focused on this stuff. Now, I think if we delve a little deeper into this, we really have 5 key objectives to meet those scenarios that Julia set out. We need a broad protection against a full range of what we would call plausible adversary threats. There are plausible threats, there are implausible threats. Some things may sound like they can be done, but physically impossible to achieve. But they have to include these evolving threats, such as cyber attacks, drone attacks, more advanced modern threats that we can see emerging with new technology, and then of course cyber attacks with quantum computing, where you could break through encryption keys, etc., much faster that can be done, or even things that were impossible in the past can be done. And these things have to be considered now that technology is evolving. That comprehensive insider protection is important, but it's also important that this is considered as a multi-layered protection. It's not just the individual personnel and how they're operated, but it's really in the entire sort of chain of how personnel are chosen, how they're trained, how they're checked, how they're monitored, how they are working together, the culture that's created. It's a and around the technology and the systems that are there as well. Of course, that creates a strong security culture. We must make sure that security is managed by organizations whose management, whose leaders, whose team members are absolutely committed to excellence in nuclear security, and they're trained properly and remains constantly on the lookout for these potential threats and vulnerabilities. And leads on to realistic assessment and testing. This really sets the scene, if you like, for how you create a security program for new nuclear and maritime. That realistic assessment and testing, which takes into account a whole load of scenarios that aren't normally seen in nuclear today, and certainly not naturally seen in shipping either. You're sort of combining these two things together. You see new scenarios coming up. So really, we need to be, we need to create these sort of in-depth creative assessments of vulnerabilities and realistic challenging tests of our abilities to defend against, what we determine to be intelligent adversaries. I mean, we can protect against, simple things, but really where there is an intelligent intent to try to achieve something nefarious is where this needs to be really tested at a high level. And then consolidating, so making sure that locations with material that can be used for bad purposes, we call this weaponizable. It's not really turning it into a weapon, so to speak, but it's really turning it into something that can cause fear and disruption in the population. And that's specifically related to things like high enriched uranium and separated plutonium from spent fuels, etc., which of course could be used for these purposes, and that must be reduced to an absolute minimum. But we think that new nuclear and some of the technologies that are chosen for this do this extremely well. So if we look then at how new nuclear could potentially provide a very different outlook and a different, if you like, foundation for the way we look at nuclear security, we need to consider the nuclear security as it is today and what it has grown up around. It's grown up around and been developed around the conventional fuel cycle. So we've got the vast majority of nuclear reactors today, either at sea in the Navy or on land for power generation, are essentially light water reactors. So they're pressurized or boiling water reactors for the most part, and they run on a very low enriched uranium fuel cycle, which of course means that they have to be refueled on a very frequent basis. The standard refueling cycle for land-based nuclear power stations is between 18 and 24 months, a year and a half to 2 years. And then you have to stop the systems. You have to open up the reactor. You have to take the fuel out. You have to, put that fuel away. You have to put new fuel in, which obviously means that, we need to transfer fresh fuels to these reactors, and we have to transport spent fuel away from the reactors, store it as well before it goes off, either for reprocessing or for disposal. And that means that we have to consider what is in that spent fuel. And of course, it contains transuranics, plutonium and other things, which of course are proliferation risk materials. And the fact that they're taking out of the reactor means that we have that security risk window that must be managed. And of course, is what this is all focused on. So if we look then at those three sort of fundamentals, the unauthorized removal of material and use and storage, that means that if in a conventional fuel cycle or conventional reactor system fuel cycle, the fuel and the coolant are entirely separate. So, the fact that we can take the fuel out and we can move that around, and also these short refueling intervals means that we have materials handling. So that's clearly one of the reasons why this is such an important issue. Sabotage of facilities and material during transport. Again, there is a fantastic track record in the nuclear transport industry of incredible strong defense in depth, in these casks, which are where this material is transported in, are indestructible and certainly not something that you can pick up and take with you. And if you were to open one of them up, then you would have a problem rather than cause a problem. Has an excellent track record. So it's specifically related to this idea that we must transport fuel to and from reactors. Sabotage of facilities, material and storage. Well, clearly, removal and the handling of this waste fuel from conventional fuel cycle means that we need to continue to provide fresh fuel supply. So you do create that vulnerability in there. In terms of new nuclear, so we're looking specifically here at the molten salt reactor. There are many other reactor technologies, of course, that changes, if you like, the outlook for this. But we have to ask ourselves, is new nuclear security different with these systems? Well, in the case of this particular reactor system, which we're describing here, which is the molten salt fast reactor, that's a molten salt liquid fueled reactor operating at fast spectrum, we are running a higher enriched fuel. It's still a low enriched fuel, but it's at a higher enrichment level. So, up to 20%. It's called high assay low enriched uranium. That's, gives us better fuel efficiency. And that means that, we have, sort of up to 10 years between the maintenance cycles. That doesn't mean that any fuel comes out of the reactor in that period, but there's maintenance cycles. So you have system stoppage and potentially new personnel moving in to look after the systems. And then 30, 40, potentially 50-year fuel cycles where no fuel is removed from the reactor core at all. And that is significant in the sense that we don't create those windows, security vulnerability windows, by fuel not leaving the core. I mean, the safest place to keep fuel, of course, is in the core of the reactor. So, importantly, in a fast reactor, of course, these transuranics, these plutonium and these things that cause proliferation risks are consumed in the reactor. They don't actually get taken out, part of the fission products in there. So fissile process in the reactor, and we avoid some of these issues related to plutonium. But in terms of removal of material and use and storage, then in a molten salt reactor like this, the fuel and the coolant is combined. So we cannot actually separate the fuel and the coolant in the reactor or even outside the reactor without a very complicated and very advanced chemical processing plant. So that means that we have this sort of defense in depth in the actual inherent part of the way that these reactors function. These very long refueling intervals, of course, with no materials handling, means that we avoid some of these security windows. Sabotage of facilities and material during transport gives us very strong defense and depth in the site. So, you have systems and reactors here which are inaccessible with fuel really at the core and no access to any of that. And of course, those reactor canisters that we would use to take off some of the sort of, the fuel cleaning products, if you like, are indestructible and extremely heavy. So, you cannot actually access this stuff. If we don't do any removal and handling of waste fuel until the end of the life of the reactor, then we avoid these security risk windows. And of course, the same thing happens when we're looking at the way that, the reactors are refueled. So with no refueling, then there's no fresh fuel required for transport. I think also just, Toby, I want to just say a little bit about, the zones around potential floating assets. This could be a floating power station or a nuclear ship, of course. We think about the emergency planning zone, and we've spoken about this a lot in previous programs. Emergency planning zone is that evacuation zone required around all reactors. Of course, with an unpressurized reactor system, we can bring this down, and we aim to bring it down to just inside the boundary of the ship. So that larger emergency planning zone that would normally exist, we would rather than start to think of really as a security planning zone. Potentially inside there, you would have detection of anything flying, aircraft or drones, divers, marine traffic in that zone, and communication about what happens in that zone is important. So it's sort of an alert zone, if you like, that triggers the security mechanisms on board the vessel or on board that power station to make sure that it's always ready for whatever happens. And that, being able to provide very powerful repellents as well as defense in depth, I think gives us a very strong case here for it being very, very difficult to get towards any of this material in any kind of way. Of course, we can provide a physical security perimeter as well. So it's really about active security, things that we can do to make sure that we always detect, that we always make sure we understand what's going on, and that our systems are alert and ready to stand against a potential threat. And then that passive security, if something was to happen and somebody were able to penetrate, if you like, that security cordon, then the access to the material, access to the reactors would be so difficult and so, we make it impossible. And then if, all the way towards the end where, it would be literally impossible to get to the material and do something with it. That would be the aim, of course, to get as close to that as possible. And then, of course, we can then zoom out a little bit and look then at remote monitoring and control. So, if you've got a fleet of these nuclear ships potentially that are moving around the world, we're thinking really about, secure communication between ship and shore, which is unhackable. We've got that cybersecurity that even covers the latest quantum computing hacking tools, central monitoring of exact locations of every single ship and reactor. That still happens today, but the ability to switch off the system, of course, wouldn't be there. Gathering data about movement, activity, what happens around the nuclear systems, etc., and always, of course, being able to do real-time inventory control. So, gathering data to make sure we understand exactly what's in the reactor at all times and nothing is diverted. Preemptive alert systems and remote guidance and mitigation support, of course, is important. If something bad was to happen, that you have that support available to the crew on board the vessel, that they know what to do and what measures to take against that potential threat. And of course, then that leads to emergency and remote control functions where you potentially then take charge of the vessel from a remote location, and the crew has not much they can do regardless in terms of where it goes. So in a sense, we think of this a bit like air traffic control. You can move towards a system where you've got security areas or security zones that are managed by certain nations that have the responsibility for those, as well as those ships that are flagged in those nations. And you pass then ships as they pass from one zone into the other. That responsibility for security may be passed, from one control center to the other, in the same way that air traffic control does. So I think we look at this from a fundamental perspective. We'll look at at the absolute in-depth detail of how these systems are implemented. Yannis is going to talk about that afterwards, and then all the way out to how do you manage, if you like, an entire fleet, monitoring, controlling, and ensuring that detection is at the forefront of everyone's mind. And I think with that, Toby, I'm going to hand back to you. So thanks very much for listening.
Well, thank you very much, Mikhail. I think some very interesting points you make there, certainly around the fuel cycle, as well as the differences between some of those active and passive security systems. And at the risk of sort of stating the obvious, I do think it's worth reiterating that point you make, that the most secure place for nuclear fuel is inside the reactor itself. And it then follows on from that the longer you can maintain that status quo, the better, really. Now, moving on, last but by no means least, I'm sitting here also with Yannis Kourasis, one of our nuclear engineers. Yannis, alongside Giulio, I know you've been considering security by design, but more specifically from the perspective of the molten salt reactor itself. So I wondered if you could elaborate a little for us on what we can learn perhaps from existing power plants, and can we optimize sort of any of those aspects for future marine installations?
Thank you very much, Toby. And it is very nice to see you all here joining another Core Power Hour. So I'm going to spend just a few moments on this title slide to lay the ground on what I'm going to be discussing today. So as you might have gathered, of course, nuclear security is a very complex and constantly evolving field. And specifically when it comes to nuclear security design, it is the industry standard to not discuss design details in public, of course, because you never know who is listening. Having that in mind, my presentation will be kept at a high level, but still, however, I will try to give you a good idea of security by design and also the physical security barriers that we have on the molten salt reactor right now. So this, Mikhail discussed and mentioned defense in depth and all regulatory frameworks. So how would the agency's security and safety frameworks look like when implemented to a reactor design? So it will look something like this. This is a great visual from the agency. I know it might look a little bit overwhelming. It showcases the defense in depth for a traditional generation 3 reactor, for example, a PWR. Here you can see the 5 levels of safety combined with the 4 barriers of security. For example, you can see as the 5th level, we have the offsite emergency response, which is something we covered on our previous webinar. And for that reason, in today's webinar, we're just going to focus on the physical security barriers. So if someone were to access the reactor, the fuel, from the outside in, the first barrier they come across is, of course, the reactor confinement. Then the primary circuit barrier, which includes, in the case of a PWR, the pressure vessel, as I understand it. And then you will get access to the fuel rods, and you will have to go through the fuel rod zircaloy cladding and the elements of the fuel matrix to finally have access to uranium oxide and fission products, etc. So if we apply the same, let's say, idea and visualization for our design of the molten salt marine reactor, which is on a floating vessel, whether that is a ship or a floating power plant, we get 8 levels of physical security barriers. So with the same logic, starting from outside in, if someone were to access the molten salt, they would have to go through, firstly, the hull and the structural components of the floating vessel. Then the next barrier would be the insulated thick steel bulkheads which surround the reactor compartment. And after that, of course, we have the reactor shielding, the confinement, which is multiple layers of materials, and another level, which are the structural support structures, the components that support that shielding. And from this point onward, all the spaces are hermetically sealed. They are airtight sealed. So after this, the next barriers would be similar to a traditional reactor, the primary circuit barrier. And then, of course, the reactor vessel boundary, which is multi-layered. It's multiple layers of steel and insulating material. And after that, we have the last barrier that touches the salt, basically comes in contact with the salt, which is the salt-facing alloys. And these alloys are very high strength typically, and they can withstand high amounts of stresses, and they are picked exactly for those kinds of properties and for being able to operate in high temperatures and high corrosive environments. And then, in my opinion, I would argue, this is up for discussion, of course, that the last barrier would be the salt temperature and its corrosive properties. Meaning that, especially in the security risk of theft, if someone were to extract and transport this material, they would have to have the tools, engineering, knowledge, and materials of a big government organization or the nuclear recycling facilities and the scrapyards that these vessels will go to at end of life. And those places, of course, are especially equipped for this kind of task. So for that reason, exactly, the top nuclear security professionals and organizations recognize the MSR design as one of the least vulnerable designs from a security perspective when it comes to theft of nuclear material and dispersal of radioactivity, and also as the only non-LWR design where the concept of significant core damage may not be strictly applicable to an MSR reactor when it comes to an attack. So all that is good. It's always good to have secure reactor design, but still nuclear security is a big challenge. So I will now try to share two examples of specifically how do we implement security by design and what are some main principles we follow in the handling of vital components. And I will start with a very vital component, which is the primary heat exchange piping. So on your right here on the images, you can see pipes in which molten salt is currently flowing through. This is in the IET in Seattle. And these pipe systems, of course, have been identified as one very obvious vital component of the system that can be a target. For that reason, we have to make sure that these systems are abundant and redundant, meaning that if damage is caused to one part of the system, there is another redundant part that will take over each operation and the whole system's operation can continue. And for the whole, the damage caused will be minimized, basically. Also, of course, these pipes are constantly monitored by various sensors. And the subsystems, the redundant subsystems, the spares, let's say, are strategically located in confined subcompartments. So the spatial distance between those subcompartments has to be maximized to mitigate the results and the consequences of any type of local damage. So this is the sort of handling we need to do to all our vital components. And lastly, another vital system is, of course, for every nuclear power plant, the instrumentations and controls system, which is, let's say, the brain of the power plant. And it is the #1 likely target for a cyber attack. Now, I am not a cybersecurity expert by any means, but we understand that from a high-level design outlook, we need to follow some very specific principles. And these would be to implement, of course, a security levels that follow a graded approach. And the data flow on these levels, in these levels, needs to be unidirectional, meaning that there is no possibility of data flowing from a low security level to a higher security level. And you get that by doing this with hardware. So the data can physically not flow from a lower security level to a higher security level. And lastly, another important principle that we understand is that the operation needs to be done in a non-runtime environment, meaning that you cannot run software in the environment that the INC is being operated on. And that rules out a whole family of known cybersecurity attacks and threats that are being used. And with that, I will conclude my part. I hope I gave you a good idea of the physical barriers and some of the considerations we have on security by design. Please send in your questions. And now we'll move on to the panel discussion. And back to you, Toby.
Yanis, thank you for that. It certainly struck me when hearing your presentation that with potentially 8 barriers of physical security between the outside world and any nuclear materials, which themselves are operating at 600 degrees Celsius, an important part of the message for an operator to sort of disseminate is that breaching the reactor compartment is not a simple process in any way at all. It's really a Russian doll sort of buried inside a labyrinth, if you like, and not something that an unscrupulous entity can really get inside and tamper with. Now, we've heard from all of our panelists individually. I'd like to open the discussion up now to include all of them together. We've examined the concept of security for new nuclear from a few different angles. And we've heard a few times about this concept of cybersecurity and the possibility of a shore-based fleet monitoring center. Would the panel be able to expand a little bit on that and explain a touch more on how a concept like that could work?
I can make a start, Toby, on that particular one. I think this is an area which the industry itself is very strongly focused on. Cybersecurity is not something specific to nuclear. It's not something that's specific to maritime. It's something that's specific to pretty much everything that touches our lives these days. And with the prospect of quantum computing that can break down crypto or sort of encrypted codes so much more quickly and more easily than what we've seen before, of course, this is a big challenge. We don't, of course, have the answers to those at this point. But I think one of the things we should consider here is how you interconnect various systems. So one of the first things I think that we need to be looking at is a closed area network on the actual vessel or floating power plant itself. So rather than the way we have it today, where you've got a certain amount of wiring that connects certain amount of systems, you really have a fully secure offline closed area network that manages the entire electronic aspect of all of these assets. And that's an area that needs a lot of research. It's an area that needs a lot of work, and it's an exciting area, I think, for somebody to take a big opportunity and then develop something there. Now, if you can then connect securely via satellite links, of course, into that closed area network, you can create, like I think Yanis has demonstrated with the physical defense in depth, you can then create cybersecurity defense in depth through that system as well. So you can approach these things in different ways. I think it's important that we recognize this is something that's going to be developing very quickly over the next few years. And it's always important to remember that, we would always be choosing the best in class systems for these things and making sure that they're not entirely automatic, that they're also there to make sure that there's always somebody there who can pull the plug out of the wall, if something is really going wrong. So I think that's probably where we're at this stage. I don't think we have any specific examples that we can give at this point, but there's an awful lot of people out there who are very focused on this, and we're engaging with this. So I'm excited about what happens in that field.
Absolutely. Yeah, I think that's quite right. And I guess a related part to this is a question on not just best in class of equipment, but best in class of sort of flag states as well, because and this is a question that's coming from Rakesh, that there's only really realistically going to be a handful of flag states operating these vessels in the future. So you would also expect that those nations will also, ships flying the flag of those nations will also be able to count on quite robust naval support as well. So there's sort of an additional active safety net there as well that perhaps we haven't gone into a lot of detail about. I don't know if you want to elaborate on that at all.
Well, I think that's absolutely right, Toby, and I think you've hit the nail on the head there. You know, if you've got the basic principle of, you know, the security being the responsibility of the state, and that flows through the flag state, because, you know, if you logically think of this as if a reactor is licensed in a particular country. Let's take the example of the United States. American technology licensed in the United States, installed on a US asset. You know, that license follows into the flag state. So the flag state would then, you know, have an agreement with the license authority to do that, and that would be responsible for that security. So that's not something that you would then be able to say, well, you know, let's export it and sell it to, you know, somebody else who is not authorized to receive that material or to receive those technologies, simply because that, you know, the entire licensing and flag state regime doesn't, export control doesn't allow for that to happen. So you can imagine, you know, certain places where the United States can export to, United Kingdom can export, France can export, you know, China, Russia can export, etc. All these countries have export control restrictions. They have, you know, the same sort of security requirement regime through the IAEA and through the international community. So, you know, this is a one where we have to consider very carefully that this is not something that, you know, can happen everywhere and can happen with everyone. It has to be controlled and managed through the licensing regime at the very core.
Understood. Thanks, Mikhail, for that. Changing topic slightly now, and perhaps this is a question for you, Giulio. We've looked today mostly at the MSR, the molten salt reactor, specifically from a security perspective, but there is a second advanced reactor type that could be applicable or suitable for marine environments as well, of course, and that's the heat pipe reactor, HPR, micro heat pipe reactor. I wondered how you might evaluate a comparison of this machine as well from a security standpoint. I mean, in simple terms, are there big differences?
Well, thank you, Toby. It's an interesting question, because the way the fuel is handled is completely different. But frankly speaking, I don't believe that from a security point of view, there will be much difference. Of course, while the molten salt reactor, especially operating the fast spectrum, has very long fuel cycle, so we don't foresee that, let's say, any tampering, any handling of the fuel or the waste is to be done during the lifetime of the reactor. For a heat pipe reactor, the reactor itself would have to be replaced, let's say around every 10 years, but still the handling of the fuel and of the spent fuel inside of the reactor would not take place on board of the vessel, but in dedicated facilities. So while there would be the need to ship the fuel and the, let's say, depleted reactors from, take them out of the vessel and bring them to a facility, there will still not be handling of any fresh or spent fuel on board. So that would, let's say, take care and greatly mitigate the proliferation issue. So yes, the technologies are different, but from a security perspective, my personal opinion is that there will not be much difference.
Understood. Thanks very much, Giulio. And just going back to the regulatory side, I guess, you know, legally speaking, a floating nuclear power plant sort of sits in the middle of the nuclear and maritime Venn diagram, if you like. You've got, you know, on one hand, sort of quite ancient laws of the sea, and yet on the other hand, you have a more contemporary set of nuclear laws that have grown up, you know, in the last few decades on the other side. And we know that sort of gap analysis is being done. And Mikhail, you mentioned that a lot of the initial work is going to be really some of it on defining, you know, what is what. You know, is it clear, for example, when a floating nuclear power plant stops being a simple unit that's in transit when it starts operating? Or do you think a new regime will sort of grow up that means that that distinction is actually no longer needed at all?
Whether it's a new regime or not, Toby, I think is up for debate. But the nuances that exist between these various iterations, we don't really have many examples of floating nuclear power. We have had them in the past, and they do exist today. We do have a lot of nuclear ships, but they're all military. So when it comes to the civilian industry, and the way that the international community looks at this, it's important that definitions are made, but that they're not academic definitions, that they're practical definitions. We do have these, specific rules, the safety code for nuclear ships, which sits, as you said, under SOLAS Chapter 8, Resolution 849/112, that's now been passed into law here in the United Kingdom. And as a result of the passing of that law, a lot of that work is now being done to make sure that this law isn't redundant from the start, but that it becomes something that we can actually use as a foundation for building out safety principles, security principles, safeguarding principles, liability principles, all these various things. And that ties back to what I think you're referring to, which is the work that's been done at the International Atomic Energy Agency on defining really, how does that agency deal with these specific things? You have reactors that are being manufactured centrally somewhere and then transported in a fueled state from one place to the other. Well, clearly, security is an important part around that because they contain fuel. They may not be operating or live, but they certainly have fuel inside them. Then you have transport in entire nuclear plants that are, entire systems with power conversion systems, instrumentation and control, etc., that can be moved around. So the purpose is a slightly different thing again, but it's really talking about cargo, moving things around as cargo, loading and discharging something for the purpose of being used elsewhere. Then you've got this idea that you integrate reactor systems on floating assets. Floating nuclear power plants could be something that doesn't even look like a ship. It could be a plug in the ocean. It could be a spar type. It could be an offshore structure. Or if it's a nuclear ship, then of course that's moving around. But you've got integrated nuclear power plants on board these floating assets. And the nuances that exist really come in transit. So moving across third-party territories or third-party territorial waters of third-party countries, and the regime that governs that, as well as these sort of uniform security and safety rules that are set down by the IEA that are then adopted by these nations, is a key part of this. So there's years and years and years of work in front of us to make sure that these things are done in a practical and almost in an agnostic way, so that we don't tie ourselves down to a specific technology or a specific application or a specific location where we have to do these things. So that it really opens up the opportunity for us to use nuclear as a way to create better, more efficient, safer energy systems than the ones we have today, and to do so in an economic and affordable manner. That's really what this is all about, right? This is not about trying to find a new way to use nuclear. It's trying to use nuclear as or rather for nuclear to take its rightful place as a way of creating safe and affordable, clean energy for everyone. And that's not something that the maritime environment and the marine environment has to play an incredibly important part of it, simply because we need central manufacturing and we need to be able to move it to where it's needed, rather than constantly building massive construction projects.
Absolutely. Yeah, it's a real paradigm shift, isn't it, that some of these new fourth generation technologies offer, and it's all very exciting. Now, I'd like to say thank you to all of our panel for your contributions today. This is the last of our online events, actually, before the end of the year. We're working on our program for 2023, and it looks like it's going to be pretty busy. So please keep an eye out on our website, our newsletter, if you haven't already signed up to it yet, and our social media channels for more details on what's coming up next in the Core Power Hour series. Now, in terms of our in-person events, which make up another element of the client program, our Singapore conference is also now very much on the horizon. It's almost exactly 2 months away. It's going ahead on the 9th of February 23. Ticket sales are open for that, so please do consider to book your place if you're based in the region, or even if you're not. It's the first ever conference to take place in Asia Pacific on new nuclear for maritime. We've got a lot to discuss. It's not just about safety and security that we've looked at here recently, but we've got a full technology briefing on the molten salt reactor and the heat pipe reactor. We've got a very interesting regulatory section which lays out some of the pathways forward. And the day is going to finish with several interactive sessions looking at some of the naval architecture we've been working on, along with some of the commercial business models. And finally, there'll be a networking drinks party going on into the evening. There's a link to the event from our homepage. There's also currently an early bird discount for those that can register before the 16th. So that has a few days left to run. So if you are interested in this, please fill out the registration form as soon as you can to take advantage of that. Or just let us know that you'd like a place and we'll do the rest at this end. Our in-person events are really the best method for interested clients and companies to take a slightly deeper dive into this topic, and that's more possible than we can get through in these shorter online programs. And that's why we're holding these in-person events at regular intervals throughout the year. So after Singapore, we'll be in the United States in June 23 and back here in London as part of London International Shipping Week in September 2023. So it really would be great to meet some of you in person at one or more of these events. But for today, all that remains for me to say on behalf of all of our panel here is to say that we hope you've enjoyed today's program. We very much appreciate you taking the time to join us. Have a good rest of the week, an excellent Christmas when it comes. Thank you very much again, and goodbye.
Thank you, everyone.